In this lecture, we're going to address probably one of the hardest parts to get our head around, and that's the forward operating environment. Like I said, our history tells us that the world is about growth, that the engineering projects are all about how do we keep up with growth, how do we keep things going. The truth is, the next century is going to be about adaptation. So, the first slide that you're looking at sort of embodies the idea we're trying to get around. Again, this analogy with safety shows us that if we can understand the hazards that we face, if we can characterize and quantify the risks, then we have the understanding of what needs to change. And that's where we can start. So this figure shows you three dimensions of risk: social, environmental, and economic. And you can see that the risks pile up if we start getting outside our adaptable zone in any one of those areas. If we start to push our carrying capacities too far, in any one area, it's bad, but all three together is quite bad. So just getting an understanding of that, what we're after. Now, we're going to move into energy because that's really sort of the crux of the problem. Of course, we've got food, water, social, there's a lot of aspects to sustainability, but in this text, we're really looking at energy, and that's all right. So let's look at oil, for example. So slide 2 shows sort of the famous wedge approach, that we have the historical consumption of an energy resource, and that's been growing and everything's been going along fine. And we have the expectation that that growth is going to continue into the future. And all you have to do is look at websites of, say, the IEA, the International Energy Association, and look at their predictions for future demand of energy, and you'll see this anticipated growth. But then if you start to look at resources, what you'll see is a decline. So the Hirsch report is a famous one of these, where they actually start looking at the oil resource and understanding that it is depleting and has been in a plateau for the last few years and is starting to decline, regardless of new fields being developed, because the big fields that were producing so much before are declining. So that produces then a wedge, right? There's a gap between our expectations and our reality, and that defines the adaptation that we have to do, especially if we're building in anticipation of that growth, if we're investing in that anticipation, and then we have to adjust to the reality that's different. So the wedge idea, gap filling those wedges, you have to look at what might bridge that gap. So slide number 3 shows an example of an idea for how to bridge the gap between oil supply and our anticipated demand for driving around. Well, if the oil is the best fuel, clearly it is, onboard energy density, that's what a mobile source of energy is. If that is, a problem, if it's declining, and we anticipate continuing to drive more and more, then we think about substituting some other form of energy for that. And so you can see on slide number 3 ideas of what you might substitute for that. Now, what you really have to be careful with is that the vertical scale on this is a log scale. And you can see there's a vast difference between oil, petrol and diesel, and the things you might substitute for that. In particular, electricity by batteries. Onboard storage with batteries is very, very small. So in other words, if you're going to go to an onboard electricity platform, you're going to have to completely rescale your thinking about how much transport you do, how much driving you do, how you do that. That's okay, you can rethink that, but you have to do it given the facts of the actual systems you're talking about, the forward operating environment. If you're going to go forward into an electric system, you have to redesign the whole system to work on electricity. The next slide, slide 4, shows the forward operating environment for oil. Now, something like peak oil. You might have heard of that. If not, you should Google it. Peak oil has become a contentious issue, even though it's quite obvious and no one actually disputes that there's a finite amount of oil. There's lots of different ways you can look at it from different points of view, and you can say, well, there will always be enough oil, and the answer to that is yes, there will always be enough oil, but there will always be less than there is today. We will never run out of oil. That's true, because it will become so expensive in the future that we'll quit pumping it. You have to understand that the reality of the forward operating environment is a world with less oil. All right, which means that if we don't adapt to using less, the price is going to adapt us. The figure that you see here is the probability of future supply. I think probability is a very good way to go because we can't predict the future, but what we're really after here is risks. And risk is the probability of something happening times the impact of that happening. All right, the next slide, slide 5, is an example of the North Atlantic cod fishery. Now, you can see that people have been eating cod from the North Atlantic for a long time, actually probably thousands of years. But then once you start to get sailing ships, the cod catch went up a bit, but then once you start to get mechanized fishing, you had exponential growth in the catch. And the catch rate clearly exceeded the capacity, the carrying capacity of that fishery for the fish to reproduce. And part of that was the destructive nature of the fishing boats, the fact that they were bottom trawlers and actually destroyed the spawning beds. So with some analysis, what you will see is that about the time that the cod fishery peaked, the predictions for what the future of that fishery would be were actually extrapolations of the past. Not possible. And the scientists of the time were telling the regulators that it's not possible and you need to really shut down how much fish people are taking or this whole fishery is going to collapse. While the fishery wasn't shut down, it's collapsed, it's gone. That sort of thing is what I think engineering needs to take control of by actually looking at the scientific information and changing the physical, technical systems to match what the scientists are saying. So if you think about it, the scientists were very clear on that the bottom trawlers was destroying the cod fishery. Couldn't it have been possible that the people producing those ships could say, look, we actually want to produce shipping vessels into the future, and the only way to do that is to have fish to catch. So we will stop producing the bottom trawlers so that we can keep selling fishing boats, right? Well, that's an idea, and it's definitely something to consider. The next slide is energy return on investment, an illustration of a concept called energy return on investment. Now we can actually use our cod fishing example here because in the year that the cod catch peaked, the highest year ever, was also the highest year of investment in those destructive fishing boats. Now, did the people who invested in those fishing boats get a return on that investment? No, because the fishery collapsed. And so what they spent to get more didn't work. They actually got less. And that's a lesson we have to learn because that's the environment we're in now. The past 100 years, we've been in an environment where if we went and spent some money to open a coal mine, to drill for oil, to drill for gas, we would get a huge return on that. We would get a lot of energy to sell and we would make money. There's a question though, what if you spend more than you get back? That's called a bad investment. And you can look at energy that same way. If it actually takes more energy to produce the energy than what you get from it, that's a really bad investment. And it turns out that the profitability of an energy investment really starts to tip over once you start to get below a return on investment in energy terms of about 10. So we can use energy return on investment, which for short is called EROI, as sort of a way to evaluate different energy options that we might be looking at for the future to tell whether they're good investments. You know, in the financial world, nobody invests in things without financial analysis to tell them whether they're going to make money on that. We need the same thing now with energy. All right, the next slide that we have here, you can see that what this is showing is the economic response to a resource as it becomes constrained. Now, basic economics tells us the law of supply and demand, that as demand goes up, if the supply doesn't go up right away, then it becomes scarce, the price goes up, and as the price goes up, that's a signal to bring in more supply. And that more supply then satisfies the demand. All right, well, that's sort of how it works, especially if we're talking about apples at a market. But if we're talking about energy, and you have built infrastructure that has a locked-in energy demand, then being able to adjust when the price of the energy goes up is called elasticity. And depending on how adaptive your system is, you may have no elasticity. So what we see in this diagram is that supply and demand sort of working for a while there is more supply to bring in at a low cost. And you sort of get these cycles of increased demand and increased supply, where the demand will grow real fast when new lower price supply comes in, and then it'll sort of level off, goes up some more. But then you can have what's called demand destruction. When the supply gets tight, new supply can't really be brought in, or if it is, it's not cheap anymore. It's actually very expensive supply. And you have a decision or adjustment or even failure of your energy systems where you can't use that anymore. It's just too expensive. It's not worth what you were doing with it, and you have demand destruction. And that's where the demand falls way down, and it may recover a bit once you get back down into the cheaper supply that you had. But essentially, this is a pattern that we've definitely seen with oil several times, and especially in 2008. And if we move on to the last slide in this little mini lecture, what we're looking at here is the idea that we can actually decide to adapt. This slide shows the idea of adaptive capacity, that if you understand the forward operating environment and you understand sort of a sustainable level of resource consumption, you can compare that to your current level of resource consumption, look at how that resource is used, and decide whether it's a good idea to engineer a transition in that resource consumption through efficiency improvements, through switching, through just reduction of waste, and potentially reduce to the sustainable level in a purposeful way, or whether you want to wait until there's a collapse of the economics of the system. So we think that it's actually important to build in adaptive capacity either way so that the economic collapse isn't as bad. But the point is that the money that you save of not having to go through these destructive cycles, you could spend on further reducing your locked-in energy demand and saving a lot of money as energy gets even more scarce. So that's what this slide is about, is understanding the idea of adaptive capacity, and that's actually what we're aiming for in a lot of the transition engineering work.